China built the most expensive architecture projects ever attempted. China built the most expensive architecture projects ever attempted. We're talking about 42 buildings that cost more than the entire GDP of countries like Portugal and New Zealand. These aren't just expensive, they're architectural experiments that rewrote the rules of what's physically possible. Structures that float on water, towers that twist into the sky, buildings carved into the earth itself. And you're about to see exactly how they pulled it off. The first one rises from frozen wetlands, where most architects said construction was impossible. Harbin Opera House. You're looking at a building that appears to be melting into the landscape. The Harbin Opera House doesn't sit on its site. It flows across it like a frozen wave. Architect Ma Yan-song designed this structure to mirror the wetlands surrounding it, creating smooth, organic curves clad in white aluminum panels that ripple across 92,000 square feet. No right angles, no flat surfaces, just continuous, sweeping curves that stretch across the frozen ground. But here's the problem. Harbin sits in northeastern China, where winter temperatures drop to -40 degrees Fahrenheit. The engineering team had to develop entirely new methods for shaping and installing those curved aluminum panels in extreme cold. Each panel connects to a steel framework beneath that had to flex and curve in 3 dimensions while remaining structurally sound under snow loads that would crush conventional roofs. They're building fluid architecture in conditions that freeze construction materials solid. The result is a structure that looks impossible, like someone poured liquid metal across the wetlands and let it freeze in mid-flow. The panels catch light differently throughout the day, making the entire building seem to shift and move, even though it's completely static. What came next made this look conservative. XIN, Cultural Center. The Xi'an Cultural Center takes a different approach. Instead of flowing curves, you're looking at angular geometry that references Tang Dynasty architecture. The building rises like a series of stacked rectangular volumes, each one slightly offset from the one below it, creating a cascading effect across the facade. The exterior is wrapped in perforated metal screens that filter sunlight and create intricate shadow patterns across the surface. But the real challenge was scale. This isn't one building, it's multiple performance venues, exhibition halls, and cultural spaces unified under a single architectural language. The cantilevered sections jut out at dramatic angles, some extending over 60 feet beyond their support columns. Engineering those overhangs required massive steel trusses hidden within the facade, transferring loads back to the core structure while maintaining those clean, geometric lines. The metal screens aren't decorative, they're structural. Each panel is precisely calculated to bear wind loads while allowing air circulation. The perforations create patterns that shift as you move around the building, making the solid structure appear almost transparent from certain angles. At night, interior lighting transforms those screens into glowing geometric grids that can be seen for miles. But geometry was about to get much more extravagant. Grand Lisboa. The Grand Lisboa in Macau looks like a golden lotus flower exploded upward into a 58-story tower. The base spreads out in petal-like forms covered in LED screens, while the tower above is wrapped in a golden exoskeleton of curved glass and metal that bulges outward as it rises. You're looking at a building designed to be seen from every angle, a glowing beacon in Macau's casino district. But engineering this shape was brutal. The tower doesn't rise straight. It expands outward in a dome-like bulge, before tapering again toward the top. That means every floor has a different diameter, and the structural steel frame had to accommodate constant curvature while supporting the weight of 58 floors. The golden facade is made of thousands of individual curved glass panels, each one custom manufactured because no two are identical. The LED-wrapped base creates its own structural challenge. Those massive pedal forms cantilever outward, requiring hidden steel supports that transfer massive loads back to the foundation. And the entire structure sits in a region prone to typhoons. So the engineering team had to design for extreme wind loads on a building specifically shaped to catch wind from every direction. The result is architecture as spectacle, a building that dominates the skyline through sheer visual excess. But extravagance was just getting started. Marisfrog Pavilion. The Marisfrog Pavilion looks like fabric frozen in stone. The facade is covered in undulating vertical fins that curve and twist across the surface, creating a rippling effect that makes the entire building appear to be in motion. Each fin is made of glass-reinforced concrete, shaped into flowing forms that reference draped textile, appropriate for a fashion retail space. But creating that illusion required parametric design software typically used for aerospace engineering. Every single fin follows a unique curved path, and no two are exactly alike. The engineering team had to calculate the structural capacity of each individual element while ensuring they work together as a cohesive system. The fins aren't just decorative, they provide shade, reduce solar heat gain, and create the building's structural rhythm. The real challenge was fabrication. Each curved concrete fin required custom formwork, meaning thousands of unique molds had to be created, used once, and discarded. The installation sequencing had to be perfect because the fins interlock at specific points, and any deviation would cascade through the entire facade. The result is a building where computational design became physical reality. Then came something that looked like it belonged in outer space: Chengdu Science Fiction Museum. The Chengdu Science Fiction Museum looks like a nebula collapsing in on itself. The building's form is dominated by a massive curved roof that swoops down to meet the ground, covered in reflective metal panels that shimmer and shift with the light. The structure appears to have no clear beginning or end, just continuous flowing surfaces that wrap around and fold into themselves. But that fluid form hides extreme structural complexity. The roof spans over 600 feet with minimal internal support, requiring a steel space frame hidden beneath those flowing surfaces. The frame had to be precisely engineered to distribute loads across compound curves while maintaining those smooth exterior lines. Every connection point had to be calculated individually because the forces change direction constantly across the surface. The metal cladding system uses thousands of triangular panels that follow the curvature, each one angled differently to create that seamless shimmer effect. Installing them required robotic precision because even tiny misalignments would be visible across those sweeping surfaces. And the entire structure had to be completed on an aggressive timeline to meet the World Science Fiction Convention deadline. What came next wasn't just a building, it was an entire artificial island, Haina Flower Island. Haina Flower Island doesn't just sit on land, the land itself had to be created first. You're looking at a massive cultural complex built on an artificial island in the South China Sea, featuring multiple performance venues clustered together like petals of a flower. Each building has a distinctive white shell-like form that curves upward, covered in flowing ribbed surfaces that catch and reflect light off the water. But building on reclaimed land presents massive engineering challenges. The foundation systems had to account for soil settlement and seismic activity, while supporting these dramatic, cantilevered roof structures. Each venue's shell is made of precast concrete ribs that span enormous distances, creating column-free interior spaces. Those ribs had to be precisely manufactured on the mainland, transported by barge, and assembled on-site with millimeter accuracy. The largest shell spans over 300 feet and cantilevers dramatically over the waterfront. Supporting that overhang required deep foundation piles driven through reclaimed soil into bedrock below the seabed, with massive transfer beams hidden within the structure. The white ribbed surfaces aren't decorative, they're the primary structural system, working like the ribs of a ship's hull to distribute loads. The luxury towers of Macau were about to make this look restrained. MGM Macau. The MGM Macau rises as a trio of golden towers, each one clad in a shimmering curtain wall of bronze-tinted glass that catches the tropical sun. The towers connect at their bases through a massive curved entrance canopy that sweeps upward like a golden wave. The facade uses thousands of individual glass panels, arranged in a grid pattern, creating vertical lines that emphasize the tower's height. But coordinating 3 towers simultaneously required extreme precision. Each tower had to rise at the same rate while maintaining perfect alignment at their connection points. The curtain wall system uses custom-engineered mullions that accommodate thermal expansion across hundreds of feet of glass critical in Macau's extreme heat and humidity. Every glass panel had to be manufactured to exact specifications because even small variations would create visible distortions across those golden surfaces. The entrance canopy presented its own challenge. That sweeping curve required steel ribs that span over 100 feet while supporting the weight of glass cladding above. The structural system had to be concealed entirely within the thin profile of the canopy, leaving no visible supports to interrupt those flowing lines. But MGM wasn't finished with Macau yet. MGM Cotai. MGM Cotai takes a completely different approach. You're looking at what appears to be massive shipping containers stacked at dramatic angles. The building consists of two towers that seem to be built from enormous rectangular boxes, each one offset and rotated from the others. The facade uses reflective panels and various metallic finishes, gold, silver, bronze, creating a patchwork effect that emphasizes the container-like geometry. But engineering stacked boxes at this scale is far more complex than it looks. Each container section cantilevers out at different angles, requiring hidden steel transfer structures to support the offset loads. The towers don't rise straight, they shift and rotate as they go up, meaning the structural core had to accommodate constantly changing floor plates while maintaining stability against typhoon winds. The metallic panels aren't randomly placed, they're precisely arranged to create visual rhythm across the stacked forms. Each panel type has different reflective properties, and the engineering team had to calculate thermal expansion for multiple metal finishes expanding at different rates. The result is a building that looks like industrial shipping infrastructure transformed into luxury architecture. Then came a building that physically loops back on itself. CCTV headquarters. The CCTV headquarters defies every instinct you have about how buildings should stand. You're looking at two towers that lean toward each other, connect at the top in a massive cantilever, and then continue down to create a complete loop. The building is literally a horizontal skyscraper suspended 400 feet in the air, and it shouldn't be possible. But the engineering required to make this work is extreme. The entire structure is wrapped in an external diagrid, a diagonal lattice of steel tubes visible across the facade. That lattice isn't decorative, it's the primary structural system, transferring loads around the loop and preventing the cantilevered section from collapsing under its own weight. Every diagonal member carries precisely calculated forces, and the pattern intensifies at stress points where loads concentrate. The cantilever spans over 240 feet and weighs thousands of tons. Supporting that required massive transfer trusses hidden within the horizontal section, distributing weight back to the leaning towers. The towers themselves had to be designed with their centers of gravity calculated for the lean. If they stood vertical, the math wouldn't work. And the entire loop had to be engineered as a single unified structure because any weak point would cascade into catastrophic failure. What came next took that loop concept and made it vertical. Guangzhou Circle. The Guangzhou Circle is exactly what it sounds like, a skyscraper with a massive circular void cut through its center. You're looking at a 33-story building shaped like a giant ring, standing on edge, with a hole in the middle large enough to fit several buildings through. The exterior is clad in copper-colored metal panels that emphasize the perfect geometry of that circle. But creating a structurally sound void at this scale is brutally difficult. The building's core can't run through the center, there is no center. Instead, the structure relies on two massive legs that support the entire ring, with internal steel trusses transferring loads around the circular void. Those trusses had to be precisely engineered. Because the forces don't flow straight down, they curve around the opening, creating tension on the inner edge and compression on the outer edge. The circular void measures over 150 feet in diameter, and maintaining that perfect geometry during construction required constant monitoring. Any settling or shift in the foundation would distort the circle. The metal cladding had to follow those curves exactly, with panels manufactured to tolerances measured in millimeters. Even slight deviations would make the circle appear warped. Then came a tower with the tallest atrium ever built, Lisa Soho. The Lisa Soho twists as it rises, split down the middle by an atrium that cuts through the entire building. You're looking at a tower where two halves spiral around a central void, creating the tallest atrium in the world, stretching 630 feet from ground to roof. The exterior is clad in floor-to-ceiling glass that emphasizes the twist, with horizontal bands wrapping around the facade at angles that change with each floor. But engineering a twisted tower split by a void required solving multiple problems simultaneously. The two halves of the building don't rise straight, they rotate as they go up, connected by sky bridges at multiple levels. The structural core had to be designed to accommodate that rotation while maintaining stability. Every floor plate is a different shape because of the twist, meaning every structural element had to be custom calculated. The atrium itself creates a massive vertical wind tunnel. Air rushing through that 630-foot shaft generates enormous pressure differentials that want to tear the building apart. The glass facade had to be engineered to withstand those forces while maintaining its twisted geometry. And the sky bridges connecting the two halves act as structural ties, preventing the halves from separating under lateral loads. What rose next became one of the most recognizable structures on Earth: Canton Tower. The Canton Tower rises 1,950 feet as a hyperboloid structure, a lattice that twists as it climbs. You're looking at a tower that starts wide at the base, narrows in the middle, then flares out again near the top, all while the steel lattice rotates around its vertical axis. The structure is wrapped in a diagonal grid of steel tubes that spiral upward, creating an impossibly complex geometric pattern visible from miles away. But building a twisted hyperboloid at this height required revolutionary engineering. The lattice isn't just aesthetic, it's the primary structural system. Every steel tube carries load, and because the tower twists, those loads are constantly changing direction as you move up the structure. The engineering team had to calculate forces for thousands of connection points, each one unique because of the rotation. The narrowest point of the hyperboloid creates the greatest structural challenge. You're concentrating the entire weight of the upper tower onto a smaller cross-section. The steel members at that waist had to be massively reinforced while maintaining the visual rhythm of the lattice. And the entire structure had to be designed for typhoon winds hitting a tower that's essentially full of holes, with wind flowing through that diagonal grid from every direction. Sports architecture was about to embrace curves in a dramatic way. Longgang Stadium. The Longgang Stadium looks like a massive crystal emerging from the ground. The roof structure consists of translucent panels supported by a web of white steel arms that radiate outward from a central point, creating a flower-like form when viewed from above. Those steel arms aren't straight, they curve and branch as they extend outward, each one covered in a white membrane that glows when lit from within. But creating a roof that appears to float required extreme structural gymnastics. The radiating arms are actually massive steel trusses, each one engineered to span hundreds of feet while supporting the weight of the translucent cladding system. The curves in those arms mean the forces don't flow in straight lines. They're constantly changing direction, requiring complex connection details at every junction point. The translucent panels use a specialized ETFE membrane, the same material used in some of the world's most advanced stadiums. But wrapping that membrane around curved steel arms while maintaining weather tightness required custom fabrication for every panel. The membrane had to be tensioned precisely because too much slack creates flutter in wind, and too much tension risks tearing. The result is a stadium that appears delicate, but is engineered to withstand extreme weather. Then came twin boulders that redefined Opera House design. Guangzhou Opera House. The Guangzhou Opera House looks like two massive boulders eroded by water and deposited on the Pearl River's edge. Designed by Zaha Hadid, the twin structures feature flowing, fractured surfaces covered in granite and glass panels that create a rippling, geological appearance. The larger volume houses the main theater, while the smaller contains a multifunctional space, and both appear to have been carved by natural forces rather than human design. But those organic curves hide brutal engineering complexity. The structures don't have traditional walls, meeting roofs. Everything flows continuously. The external skin uses thousands of triangulated glass-reinforced gypsum panels, each one uniquely shaped to follow Hadid's sculpted forms. Those panels had to be manufactured using 5-axis CNC machines because the compound curves couldn't be created with conventional methods. The granite cladding follows similar complexity. The stone panels wrap around curves that shift in 3 dimensions, requiring each piece to be custom cut and precisely positioned. The structural steel frame beneath had to accommodate those flowing forms while supporting the weight of all that stone and glass. Any errors in the frame would ripple through the entire facade, making the organic shapes appear distorted. Football stadiums were about to embrace even more dramatic canopies. Chengdu Fenghuangshan Football Stadium. The Chengdu Fenghuangshan Football Stadium is topped by a floating cloud. The canopy appears to hover above the seating bowl, supported by massive petal-like structures that curve upward and outward. The roof's underside is clad in white perforated metal panels that create a billowing, fabric-like appearance, while the exterior features a sleek silver finish that reflects the sky. But making a canopy appear weightless while spanning a 60,000-seat stadium required massive hidden engineering. The pedal supports are actually enormous steel trusses, some reaching heights of over 200 feet. Each pedal curves in multiple directions simultaneously, meaning the structural forces spiral through the supports rather than flowing straight down. The connection points where pedals meet the seating bowl had to transfer massive loads while maintaining those elegant curves. The perforated metal panels covering the underside serve dual purposes. They reduce wind resistance by allowing air to flow through the canopy, and they conceal the complex truss network above. Each panel had to be shaped to follow the compound curves while maintaining consistent perforation patterns. The result is a stadium where the roof appears to float like an actual cloud, defying the massive structural system holding it up. Then came a hotel complex that redefined hotel architecture. Sunrise Kempinski Hotel. The Sunrise Kempinski Hotel is shaped like a giant rising sun. You're looking at a circular building that stands 318 feet tall, clad entirely in glass panels that reflect the sky, mountains, and lakes surrounding it. The design takes inspiration from the symbolism of the sun rising over Yanqi Lake, representing harmony, unity, and infinity in Chinese culture. Over 10,000 individual glass panels wrap around the circular form, spanning nearly 200,000 square feet of reflective surface. But creating a perfectly circular glass facade at this scale required extraordinary precision. Each of the 10,000 panels had to be angled. Specifically, the top sections reflect the sky, the middle reflects the nearby Yan Mountains, and the bottom reflects the lake below. The structural system uses concrete-filled tubular steel columns arranged in an arc around the building's exterior, with the entire framework supporting that massive glass curtain wall. Installation required GPS locators to determine the spatial coordinates of each corner point in 3 dimensions, because even millimeter deviations would be visible across the curve. The building starts from a 3rd-floor base, shaped like a cloud, so the circular structure appears to be lifted upward the cloud, lifting the sun. The entrance is designed to look like a fish's mouth, symbolizing prosperity in Chinese culture. The result is a building that changes appearance throughout the day as light shifts across those 10,000 reflective panels. Dual theaters were about to take geometric symbolism to extremes. Hangzhou Grand Theater. The Hangzhou Grand Theater consists of 2 distinct buildings, one representing the sun, the other the moon. The larger theater is a massive golden sphere that appears to hover above the ground, while the smaller performance hall sits beside it as a crescent-shaped structure. Both buildings are positioned on the edge of West Lake, creating a dramatic silhouette against the water. The Golden Dome is clad in reflective metal panels that catch sunlight during the day and glow from internal lighting at night. But engineering a perfect sphere at this scale presented massive structural challenges. The dome doesn't rest on a continuous foundation. It's supported by strategic load-bearing points that make it appear to float. The steel framework beneath the golden cladding had to distribute the dome's weight while maintaining that seamless spherical geometry. Every panel on the surface curves in multiple directions, requiring custom fabrication for thousands of individual pieces. The crescent building beside it uses a similar panel system, but follows a completely different curvature. The 2 structures had to be engineered independently while maintaining visual harmony. Different structural systems, different geometries, but unified by their reflective metal cladding. The result is a theater complex where celestial symbolism drives the entire architectural form. Then came performance halls, inspired by nautical forms. Jiangsu Grand Theater. The Jiangsu Grand Theater features sweeping sail-like forms that curve upward from the ground. You're looking at a building where multiple wing-shaped structures rise at dramatic angles, clad in white panels that emphasize the flowing geometry. The sails appear to billow in the wind, creating a sense of movement frozen in architecture. Each sail follows a different curve, intersecting and overlapping to create a complex sculptural form. But engineering those billowing sails required solving extreme structural problems. Each sail is supported by internal steel trusses that follow the compound curves while bearing the weight of the exterior cladding. The sails cantilever outward at steep angles, creating massive overhangs that required careful load calculations. The connection points where multiple sails intersect had to transfer forces in multiple directions simultaneously while maintaining the smooth exterior surfaces. The white cladding system uses thousands of panels that wrap around those curves, each one custom-shaped to follow the sail geometry. The panels had to be manufactured with precise tolerances because any misalignment would be immediately visible across those sweeping white surfaces. The result is a performance hall that looks like a fleet of ships captured mid-voyage. Science museums were about to embrace even more futuristic forms. Shenzhen Science and Technology Museum. The Shenzhen Science and Technology Museum looks like it arrived from another dimension. The building features a crystalline structure with sharp angular forms that jut out at dramatic angles, clad in reflective metal and glass panels. The facades consist of faceted geometric planes that create a fragmented, prismatic appearance, like a massive crystal that's been fractured and reassembled. No two faces are parallel, and the entire structure appears to defy conventional geometry. But creating this crystalline chaos required extreme precision. Every faceted plane had to be engineered individually because the forces acting on angled surfaces don't follow standard patterns. The steel framework beneath had to accommodate constantly changing angles while maintaining structural integrity. The connection points where different planes meet required custom fabricated joints that could handle forces coming from multiple directions. The reflective cladding system uses panels angled to create that fragmented appearance. Each panel catches light differently, making the entire building shimmer and change throughout the day. The glass sections are positioned strategically to allow natural light into exhibition spaces, while the metal panels provide solid enclosure. Installing those panels required constant three-dimensional surveying because even slight deviations would destroy the geometric precision. Then came theaters that emerged from the sea itself. Zhuhai Grand Theater. The Zhuhai Grand Theater consists of two shell-like structures rising from an artificial island in the South China Sea. You're looking at buildings that resemble massive seashells washed ashore, with curved white forms that sweep upward and outward. The larger shell houses the opera hall, while the smaller contains a multifunctional theater. Both structures feature flowing organic curves covered in white ribbed surfaces that create a rippling, wave-like texture across the facades. But building on an artificial island in the ocean created brutal engineering challenges. The foundations had to be driven deep through reclaimed land into bedrock beneath the seabed, accounting for soil settlement and seismic activity. The shell forms themselves required complex structural systems, precast concrete ribs that span enormous distances while following those organic curves. Each rib had to be precisely manufactured on the mainland, transported by barge, and assembled on-site with millimeter accuracy. The white-ribbed surfaces aren't decorative, they're the primary structural system, working like the ribs of an actual shell to distribute loads across the curved forms. The ribs cantilever dramatically over the waterfront, requiring hidden steel reinforcement within each element. The entire complex had to be engineered to withstand typhoons and saltwater corrosion while maintaining those delicate organic curves. What came next took the concept of building on water even further. Sheraton Huzhou Hot Spring Resort. The Sheraton Huzhou Hot Spring Resort is a massive ring-shaped building that straddles a lake. You're looking at a structure that forms a complete horseshoe, with the open end facing the water and the curved sections rising directly from the lake surface. The building is clad in reflective glass and white panels that follow the continuous curve, creating a shimmering loop that's reflected in the water below. The entire structure appears to float, with no visible support where it meets the lake. But engineering a building that sits partially in water required solving massive foundation challenges. The sections rising from the lake needed underwater foundations capable of supporting a multi-story curved structure while resisting constant water pressure and wave action. The structural system uses deep pilings driven into the lakebed, with waterproofed foundation walls that create a dry zone within the water itself. The curved form meant every foundation point carried different loads, because the geometry constantly changes. The glass curtain wall had to wrap continuously around that horseshoe curve while maintaining weatherproofing where the building meets the water. The lower sections required specialized waterproof ceiling systems because any breach would flood the interior spaces. The result is a hotel where half the building sits on land and half emerges from the lake, unified by that continuous curved glass facade. Then came a project that literally grew a mountain in the city, 1,000 trees. Shanghai. The 1,000 Trees project looks like a mountain range erupted in downtown Shanghai. You're looking at a massive mixed-use complex where over 1,000 concrete columns rise at various heights, each one topped with planted terraces that cascade down the structure. The columns are arranged in an irregular pattern, creating a rocky, mountainous silhouette covered in vegetation. Trees and plants grow from every level, transforming the concrete structure into a vertical forest. But creating a building where every column supports living trees required revolutionary structural engineering. Each of the 1,000-plus columns had to be individually designed because they rise to different heights and support different loads. The planted terraces on top of each column required waterproofing systems, drainage networks, and irrigation infrastructure, all integrated into the structural concrete. The columns had to be thick enough to house utilities while maintaining the aesthetic of natural rock formations. The planting system required soil depths capable of supporting mature trees on elevated platforms hundreds of feet in the air. The structural engineers had to calculate additional loads for fully saturated soil, root systems, and the weight of mature vegetation. Each terrace needed drainage that prevented water from damaging the structure below while ensuring plants received adequate moisture. The result is architecture that blurs completely into landscape, a building that's also a forest. What came next was the largest spherical structure in the world. Hilton Huzhou, Nangshun. The Hilton Huzhou Nanshun is a 19-story spherical building rising from the edge of a lake. You're looking at a perfect sphere with a diameter of 321 feet and a height of 321 feet, making it one of the largest spherical buildings in the world. The entire structure is clad in glass curtain walls that wrap around the curved surface, reflecting the sky, mountains, and surrounding water. The design is inspired by the rising sun emerging from the lake, but engineering a habitable sphere at this scale required solving problems that don't exist in conventional buildings. Every floor plate is circular, but with a different diameter as you move up and down through the sphere. The structural system had to support 19 floors while following that perfect spherical geometry, meaning no two floors have the same structural grid. The glass curtain wall required thousands of custom curved panels, each one shaped to follow the compound curvature of the sphere. The foundation system had to support the enormous point loads where the sphere meets the ground, with all the weight of a 19-story building concentrated on a relatively small contact area. The result is a hotel where guests look out through spherical floor-to-ceiling windows, and the entire building appears to float above the lake like a giant pearl or rising sun. Bamboo-inspired towers were about to reshape city skylines. China Resources Tower. The China Resources Tower rises like a massive bamboo shoot sprouting from the Shenzhen skyline. You're looking at a super tall skyscraper that reaches over 1,300 feet, with its facade divided into vertical sections that taper and bulge like segments of bamboo. The glass curtain wall is interrupted by horizontal bands that wrap around the tower at regular intervals, mimicking the nodes where bamboo segments connect. The entire structure curves gently as it rises, creating a subtle organic quality in what's otherwise a vertical tower. But translating bamboo's organic form into a super tall required extreme structural engineering. The tapering sections mean the floor plates change size as you move up the tower, requiring a structural system that could accommodate varying loads at different heights. The horizontal bands aren't decorative, they're structural transfer floors that redistribute loads and provide lateral bracing. Each band required massive steel trusses hidden within the facade, strong enough to support the weight of multiple floors above and below. The glass curtain wall had to follow those curves and tapers while maintaining the illusion of continuous vertical segments. The panels change size and angle at each level, requiring custom fabrication throughout the tower. The horizontal bands use different cladding materials that emphasize the segmented bamboo concept, creating visual rhythm up the facade. The result is a skyscraper that brings natural forms to extreme height, organic inspiration executed in steel and glass. National landmarks were about to make the boldest architectural statements. National Center for the Performing Arts. The National Center for the Performing Arts in Beijing is a massive titanium and glass dome that appears to float on water. You're looking at an elliptical structure that measures 692 feet long and 476 feet wide, rising 150 feet high. The entire dome is clad in titanium panels and glass sections that create a shimmering, reflective surface. The building sits in the middle of an artificial lake, with no visible entrance above. Water access is through an underwater tunnel that emerges inside the dome. But creating a dome that sits on water required extraordinary engineering. The structure needed a foundation system, capable of supporting the massive weight while sitting partially submerged. The titanium shell uses over 18,000 individual panels, each one curved to follow the precise elliptical geometry. The glass sections are positioned strategically to allow natural light into performance spaces while maintaining the dome's seamless exterior. The underwater entrance tunnel required waterproofing systems that could handle constant submersion while allowing thousands of visitors to pass through daily. The dome itself had to be engineered to resist wind loads on its curved surface, while the artificial lake created additional challenges with water pressure against the lower portions of the structure. The result is a performance hall that appears to be a giant egg floating on water, visible from across Beijing as a gleaming titanium landmark. Museums were about to become architectural statements themselves. Museum of Contemporary Art and Planning Exhibition. The Museum of Contemporary Art and Planning Exhibition in Shenzhen features a twisted, angular form that looks like folded geometric planes. You're looking at a building where sharp-edged volumes intersect at dramatic angles, clad in white panels and glass that emphasize the fractured geometry. The structure appears to be multiple buildings colliding mid-air, with each section tilted at different angles. The facade uses a combination of solid white surfaces and transparent glass sections that create a dynamic interplay of opacity and openness. But engineering those colliding volumes required solving extreme structural challenges. Each angled section had to be independently supported while connecting to adjacent volumes at non-perpendicular angles. The structural steel framework needed custom fabricated joints at every intersection point because standard connections don't work when surfaces meet at compound angles. The load paths don't flow vertically, they zigzag through the twisted forms, requiring careful calculation of forces at every junction. The white cladding system had to wrap around those angular surfaces while maintaining crisp edges where different planes meet. Any deviation in the angles would be immediately visible across the geometric facade. The glass sections required custom frames that could accommodate the tilted surfaces while maintaining weatherproofing. The result is a museum where the architecture itself becomes an exhibit, a building that challenges conventional notions of how structures should stand. Performance venues inspired by organic forms were reaching new levels of complexity. Changsha, Meishihu, Grand Theater. The Changsha Meishihu Grand Theater consists of two petal-like structures that appear to bloom from the edge of Meishihu Lake. Designed by Zaha Hadid, you're looking at flowing white forms that curve and sweep upward, covered in smooth panels that create an organic, almost liquid appearance. The larger petal houses the main theater, while the smaller contains a multifunctional hall. Both structures feature sweeping curves with no straight lines or right angles. Pure sculptural forms that look like they've been shaped by natural forces. But translating Hadid's organic vision into buildable structure required revolutionary engineering. The flowing forms meant every structural element followed unique curves, no repetition, no standard components. The white exterior uses glass-reinforced concrete panels, each one custom fabricated to follow the compound curves. The panels had to be manufactured using advanced molding techniques because the surfaces curve in multiple directions simultaneously. The structural framework beneath had to support those dramatic curves while creating column-free interior spaces for the performance halls. Steel trusses follow the flowing geometry, with connection points calculated individually because forces change direction constantly across the curved surfaces. The buildings sit on the lake edge, requiring foundations that could handle both the sculptural forms above and the waterfront location below. The result is architecture that appears weightless, solid concrete, and steel made to look like frozen petals floating on water. Stadium canopies were about to reach unprecedented scale. Hangzhou Sports Park Stadium. The Hangzhou Sports Park Stadium is topped by a massive lotus flower-inspired canopy that appears to bloom over the seating bowl. You're looking at a roof structure where petal-shaped sections radiate outward from a central point, each one curving upward and outward in a sweeping arc. The petals are clad in white panels on the underside and a translucent membrane on top, creating a canopy that glows when lit from within. The entire structure spans over 80,000 seats, with the lotus petals extending far beyond the seating bowl to provide weather protection. But engineering a lotus canopy at stadium scale required extreme structural gymnastics. Each petal is supported by massive steel trusses that curve in 3 dimensions. They're not just arcing upward, they're also twisting as they extend outward. The trusses had to be precisely calculated because the forces spiral through the curved members rather than flowing in straight lines. The connection points where petals meet at the center required enormous steel nodes capable of handling loads from multiple directions simultaneously. The translucent membrane covering the petals uses ETFE panels tensioned across the curved steel framework. Each panel had to be custom shaped to follow the petal geometry while maintaining proper tension. Too loose and it flutters in wind, too tight and it risks tearing. The white underside cladding creates a smooth, continuous surface that hides the complex truss network above. The result is a stadium where the roof doesn't just provide shelter, it transforms the entire structure into a giant blooming flower visible across Hangzhou. Then came performance halls that merged multiple architectural traditions. Suzhou Bay Grand Theater. The Suzhou Bay Grand Theater sits on a peninsula extending into the lake, featuring a design that fuses traditional Chinese architectural elements with contemporary forms. You're looking at a complex of interconnected buildings with sweeping rooflines that curve upward like traditional temple eaves, but executed in modern materials: glass, steel, and white cladding. The structures cascade down toward the water, with each building's roof flowing into the next, creating a rhythmic series of curves that echo classical Chinese architecture while remaining distinctly modern. But merging traditional forms with contemporary scale required careful structural engineering. Those upward curving roof lines aren't just aesthetic, they had to be structurally sound while spanning large performance spaces below. The steel framework supporting each curved roof follows complex geometries that reference traditional timber construction but uses modern materials capable of spanning far greater distances. The connection points between buildings required flexible joints that allow independent movement while maintaining the visual flow from one structure to the next. The peninsula location meant foundations had to be driven through soft lakebed soils into stable ground below. The buildings sit partially over water, requiring waterproofed foundation walls and systems to handle constant moisture exposure. The glass and white cladding wrap around those traditional roof forms, creating surfaces that shift between transparency and opacity. The result is a theater complex where ancient architectural language meets contemporary engineering familiar forms executed at unprecedented scale. Super tall towers inspired by natural forms were transforming regional skylines. Hefei Feikui Tower. The Hefei Feikui Tower rises as a twisted skyscraper inspired by jade crystal formations. You're looking at a tower that rotates as it climbs, with faceted glass facades that catch light like a cut gemstone. The building reaches over 800 feet tall, with its exterior divided into angular geometric planes that shift orientation as the tower spirals upward. The glass curtain wall uses green-tinted panels that reference jade feikui means jade in Chinese, creating a shimmering emerald appearance against the sky. But engineering a twisting tower with faceted facades required solving multiple structural challenges simultaneously. The rotation means every floor plate is oriented differently, so the structural core had to accommodate constant angular changes while maintaining stability. The faceted exterior isn't just glass mounted on a frame. The geometric planes are part of the structural expression, with each facet requiring precisely calculated angles to create that crystalline appearance. The green-tinted glass panels change in size and angle as you move up the tower, following the twist and the faceted geometry. Every panel had to be custom manufactured because the rotation means no two floors are identical. The structural system uses reinforced concrete cores with steel outriggers that tie into the exterior frame, but those connections had to account for the changing angles. The result is a super tall that looks like a massive jade crystal growing from the Earth's geometric precision meeting organic inspiration at extreme height. Then came the most iconic stadium ever built, Beijing National Stadium. The Beijing National Stadium, known worldwide as the Bird's Nest, is a steel lattice structure that wraps around the seating bowl in a seemingly random pattern. You're looking at a stadium where the exterior structure is a woven network of steel beams that crisscross and intersect at thousands of points, creating an organic nest-like appearance. The lattice consists of steel sections, weighing over 42,000 tons, with no two beams following the same path. The structure rises 340 feet high and spans over 1,000 feet across, all held together by this chaotic-looking but precisely engineered web. But creating organized chaos at this scale required revolutionary structural engineering. Every single steel beam in that lattice carries load, and because they intersect at irregular angles, each connection point required custom fabrication. The engineers had to calculate forces for thousands of unique joints where beams meet at non-standard angles. The lattice isn't decorative, it's the primary structural system, with loads flowing through the woven pattern rather than through traditional columns and beams. The randomness is an illusion. Computer modeling determined the exact position and angle of every beam to ensure structural integrity while maintaining that organic appearance. The steel sections curve and twist as they weave through the lattice, requiring advanced fabrication techniques to bend massive structural members into precise shapes. The result is a stadium where structure becomes sculpture, an engineering feat disguised as artistic chaos that became the defining image of the Beijing Olympics. Regional cities were building their own mega-stadiums. Lanzhou Stadium. The Lanzhou Stadium features a dramatic canopy with undulating curves that ripple across the structure like waves. You're looking at a roof that doesn't follow a single geometric form. Instead, it flows in multiple directions with peaks and valleys creating a dynamic, mountainous silhouette. The canopy is supported by massive white structural ribs that arc upward and outward, clad in panels that emphasize the flowing geometry. The entire roof appears to be in motion, frozen mid-wave above the 60,000-seat bowl. But engineering a canopy that curves in multiple directions simultaneously created extreme structural complexity. Each rib follows a different path, arcing at different angles and reaching different heights. The structural steel framework had to be custom designed for every single rib because no two are identical. The forces don't flow uniformly, they concentrate at different points depending on the curve, requiring varied reinforcement throughout the structure. The cladding system had to wrap around those compound curves while maintaining weather tightness across the entire roof. Panels change shape and angle constantly as they follow the undulating surface, requiring thousands of custom fabricated pieces. The canopy had to be engineered for extreme wind loads because the curved surfaces catch wind from multiple directions, creating unpredictable pressure patterns. The result is a stadium where the roof dominates the design. A sculptural form that transforms a sports venue into a regional landmark. Then came a hotel built where no hotel should exist. Intercontinental Shanghai Wonderland. The Intercontinental Shanghai Wonderland is built into the side of an abandoned quarry, with the majority of the hotel descending below ground level. You're looking at a structure that clings to a sheer rock face, with 16 floors extending downward into the pit 2 floors above ground, and 14 floors carved into the quarry wall. The facade follows the natural curve of the rock face, with glass and concrete terraces stepping down the cliffside. The lowest 2 floors are actually underwater, submerged beneath a lake at the quarry bottom. But building downward into a quarry created engineering challenges that don't exist in conventional construction. The structure had to be anchored directly into the rock face, with foundations drilled deep into the quarry walls to prevent the building from sliding or collapsing. Each floor cantilevers outward from the cliff, requiring massive structural supports embedded in solid rock. The glass facades had to withstand not just wind loads, but also potential rockfall and seismic activity. The underwater floors required specialized waterproofing systems and reinforced concrete walls capable of handling constant water pressure. The glass viewing areas in those submerged levels needed engineering that could resist the weight of water pressing against them while maintaining transparency. Vertical circulation through 16 floors descending into Earth required structural cores strong enough to handle the unique load distribution of a building that goes down instead of up. The result is a hotel that inverts every principle of conventional architecture. A skyscraper built in reverse, plunging into the earth rather than rising toward the sky. Macau's casino architecture was about to push structural boundaries even further. Morpheus Hotel, Macau. The Morpheus Hotel in Macau is a 40-story tower with a white exoskeleton that wraps around the building in a continuous flowing pattern. Designed by Zaha Hadid, you're looking at a structure where the exterior framework curves and twists around two massive voids that cut through the entire height of the building. The exoskeleton consists of white structural members that weave around these voids in an organic three-dimensional lattice. No traditional internal columns support this tower. The entire load is carried by that external framework. But creating a skyscraper with giant voids punched through it required structural engineering that had never been attempted before. The exoskeleton uses a free-form design with no repeated geometric patterns. Every structural member follows a unique curve through three-dimensional space. The steel framework had to be precisely calculated because loads flow around those voids rather than straight down through the building. Each connection point where structural members meet required custom fabrication because they intersect at constantly changing angles. The two voids measure over 100 feet across and extend through multiple floors, creating dramatic interior spaces but eliminating traditional load paths. The structural engineers used advanced computer modeling to map how forces would flow through the curved exoskeleton, then fabricated each steel section to tolerances measured in millimeters. The white cladding wraps around those curves, emphasizing the sculptural quality of the structure. The result is Zaha Hadid's final completed building, a tower that appears to have been carved from solid material rather than built from components. Themed architecture was reaching billion-dollar scale. Sanya Beauty Crown Hotel Complex. The Sanya Beauty Crown Hotel Complex consists of multiple tower buildings shaped like crowns rising from a tropical resort. You're looking at structures where the upper floors flare outward in a crown-like formation, with each building featuring ornate architectural detailing that references royal headpieces. The towers are connected at their bases and use gold and reflective cladding that creates a shimmering, jewel-like appearance. Some of the crown structures rotate slowly, adding kinetic movement to the architectural spectacle. But engineering buildings with rotating crown sections required solving problems that don't exist in static architecture. The rotating portions sit on massive turntable mechanisms capable of supporting multiple floors of hotel rooms while allowing continuous slow rotation. The structural systems had to separate the rotating sections from the fixed base, with all utilities, water, power, data running through rotating joints that maintain connections during movement. The crown-shaped flared tops create extreme cantilevers, where upper floors extend far beyond the tower cores below. Those overhangs required massive transfer structures hidden within the buildings, distributing loads back to the central cores while maintaining the ornate crown appearance. The gold cladding and decorative elements had to be lightweight, yet durable enough to withstand tropical storms while rotating. The result is a hotel complex where architecture becomes spectacle buildings, designed to dazzle with both form and movement, pushing the concept of themed architecture to structural extremes. Then came flowing forms that redefined urban mixed-use development. Galaxy Soho, Beijing. Galaxy Soho in Beijing consists of 5 separate buildings connected by flowing bridges and platforms, creating a continuous organic form. Designed by Zaha Hadid, you're looking at structures with no straight lines or corners, just flowing curves that ripple and merge across the entire complex. The white facades undulate in waves, with horizontal bands wrapping around the curved surfaces. The buildings appear to melt into each other, connected at multiple levels by swooping pedestrian bridges that follow the same flowing geometry. But creating 5 buildings that flow together as one required extraordinary structural coordination. Each tower has a different footprint and height, yet they all share the same curved architectural language. The structural cores had to support irregular floor plates that change shape on every level because of the continuous curves. The connecting bridges aren't simple walkways, they're structural elements that span significant distances while following compound curves, requiring custom steel frameworks that could handle both the curvature and the loads. The white cladding system uses aluminum panels that wrap around those flowing surfaces in horizontal bands. Each panel follows the curves precisely, with thousands of custom-shaped pieces creating the illusion of continuous flowing surfaces. The panels had to be manufactured and installed with extreme precision because any misalignment would be visible across those sweeping white curves. The result is a retail and office complex that looks like liquid architecture, frozen in motion. 5 buildings, unified by curves that erase the boundaries between separate structures. Super tall mixed-use towers were reaching new heights in regional cities. Greenland Hangzhou Century Center. The Greenland Hangzhou Century Center is a super tall tower that rises over 800 feet, dominating the Hangzhou skyline. You're looking at a tower with a tapering form that narrows as it climbs, clad in a glass curtain wall with subtle vertical fins that emphasize its height. The facade uses alternating bands of reflective and transparent glass, creating a rhythmic pattern that changes appearance throughout the day. The tower's profile curves gently, avoiding the rigid rectangular form of conventional skyscrapers. But engineering a tapering supertall required solving structural challenges unique to buildings that change width as they rise. The floor plates decrease in size at higher levels, meaning the structural core had to accommodate constantly changing dimensions while maintaining stability against wind loads at extreme height. The tapering form actually creates greater wind exposure because there's less mass at the top to counterbalance lateral forces. The glass curtain wall had to follow that taper while maintaining consistent visual rhythm. The vertical fins aren't just aesthetic, they're structural elements that help reduce wind loads and provide additional rigidity to the facade system. Each fin had to be precisely positioned to maintain the pattern as the building narrows. The result is a super tall that uses subtle curves and tapering to soften what could have been a rigid glass tower, bringing elegance to extreme height while reshaping the Hangzhou skyline. Corporate campuses were about to make bold architectural statements. DJI Sky City. DJI Sky City features multiple towers that appear to hover above the ground, connected by elevated walkways and sky bridges. You're looking at a campus where sleek glass and metal towers seem to float, with minimal ground-level contact creating the illusion of levitation. The buildings use cantilevered sections that extend outward from narrow bases, creating dramatic overhangs. The facades are clad in reflective glass panels, with metallic accents that reference drone technology, clean lines, precision engineering, and a futuristic aesthetic appropriate for a drone manufacturer's headquarters. But making buildings appear to hover required extreme structural engineering at the base. The narrow support points concentrate enormous loads onto small foundation areas, requiring deep pilings and massive transfer structures hidden below grade. The cantilevered sections extending outward from those narrow bases required internal steel trusses capable of handling the leverage forces. The farther the overhang, the greater the structural demands. The sky bridges connecting the towers aren't simple walkways, they're structural elements spanning significant distances while appearing lightweight and minimal. Each bridge required precise engineering to handle both its own weight and the pedestrian loads while maintaining that floating aesthetic. The reflective glass facades wrap around the cantilevered forms, emphasizing the sense of weightlessness despite the massive structural systems hidden within. The result is a corporate campus that embodies its product architecture that appears to defy gravity, just like the drones DJI manufactures. Entertainment mega-resorts were becoming cities unto themselves. Studio City Macau. Studio City Macau is a massive entertainment complex, dominated by a golden tower with a figure-8 Ferris wheel integrated into its facade. You're looking at a building where 2 enormous glass spheres, each containing observation pods, move along a track that forms a figure-8 pattern on the exterior of the tower. The building itself is clad in golden glass and metallic panels that create a shimmering appearance. The Ferris wheel isn't an addition, it's embedded into the architecture, with the structural framework supporting both the building and the rotating observation system. But integrating a moving Ferris wheel into a tower facade required engineering that merged architecture with mechanical systems. The figure-8 track is a structural element that had to be precisely calculated to handle the weight of the moving pods while resisting wind loads on the exposed wheel system. The building's structural frame had to accommodate the wheel's support points, transferring loads from both the static tower and the dynamic wheel system into the foundations. The golden glass curtain wall wraps around the tower while leaving space for the Ferris wheel to rotate. The facade transitions from solid cladding to open framework where the wheel integrates, requiring careful detailing to maintain weatherproofing while allowing mechanical movement. The observation pods travel along that figure-8 path, requiring precision engineering to ensure smooth operation while remaining structurally stable at extreme height. The result is a resort where the architecture becomes the attraction, a building that's also a kinetic sculpture, blurring the line between structure and entertainment. Science centers were embracing organic architectural forms. Guangdong Science Center. The Guangdong Science Center is shaped like a giant kapok flower, Guangzhou's city symbol, with petal-like structures radiating from a central core. You're looking at a complex where multiple curved volumes extend outward, each one representing a petal of the flower. The structures are clad in metallic silver panels that create a futuristic appearance, contrasting with the organic flower inspiration. The petals vary in size and height, creating a dynamic silhouette where some sections soar upward while others curve closer to the ground. But creating multiple petal-shaped buildings that all connect to a central core required extraordinary structural coordination. Each petal is essentially a separate structure with its own curved geometry. Yet they all meet at connection points that had to transfer loads from multiple directions simultaneously. The steel framework supporting each petal follow unique curves, no repetition, no standard components. Every connection had to be custom engineered because the petals meet at different angles. The metallic cladding had to wrap around those organic curves while maintaining weatherproofing at the seams where petals meet. The panels follow compound curves, requiring thousands of custom-shaped pieces that change size and angle as they wrap around the petal forms. The interior spaces between petals create covered atriums and circulation areas, requiring additional structural elements that span between the curved volumes. The result is a science center where the architecture mirrors natural forms, a building designed as a flower that required engineering as complex as nature itself. Mixed-use complexes were reaching unprecedented architectural ambition. Nanjing Zendai Himalayas Center. The Nanjing Zendai Himalayas Center is a massive mixed-use complex inspired by mountain ranges, with multiple interconnected buildings that rise and fall like peaks and valleys. You're looking at structures clad in white and metallic panels that create a rippling, undulating facade across the entire development. The buildings vary in height, creating a skyline that mimics the jagged profile of the Himalayas. Curved bridges and elevated walkways connect the towers at multiple levels, and the facades feature flowing lines that wrap horizontally around the structures. But creating a development where every building references mountainous terrain required coordinating multiple structural systems under a unified design language. Each tower has a different height and footprint, yet they all share those flowing horizontal lines that create visual continuity. The structural cores had to accommodate irregular geometries, while the connecting bridges required precise alignment between independently moving towers. Those bridges aren't decorative, they're structural spans that had to account for differential movement as each tower settles and sways independently. The cladding system uses panels that follow the undulating surfaces, creating that mountain range silhouette. The horizontal bands wrap around curves and angles, requiring thousands of custom fabricated pieces that maintain rhythm across the entire complex. The varying heights meant engineering different wind load responses for each tower while ensuring the visual language remained consistent. The result is a mixed-use development that functions as multiple buildings but reads as a single mountainous landscape architecture that transforms an urban block into a sculpted topography. Then came a project that merged finance with cultural preservation. Shanghai Bund Finance Center. The Shanghai Bund Finance Center features a kinetic facade where massive aluminum panels actually move throughout the day. You're looking at a tower where the exterior isn't static. Motorized louvers rotate and shift position, responding to sunlight and creating a constantly changing appearance. The facade consists of thousands of individual panels arranged in a geometric pattern, each one capable of independent movement. As the sun moves across the sky, the panels adjust their angles, creating shifting patterns of light and shadow across the building's surface. But engineering a moving facade at this scale required integrating architectural and mechanical systems in unprecedented ways. Each panel needed its own motorized mechanism capable of rotating while withstanding wind loads at height. The structural framework had to support both the weight of the panels and the mechanical systems driving them, with electrical and control systems running throughout the facade. The panels had to be precisely balanced so motors could move them efficiently while maintaining structural integrity. The control system coordinates thousands of individual panels, adjusting their positions based on sun angle, time of day, and interior climate control needs. Each panel's movement had to be calculated to prevent collisions with adjacent panels while maintaining the geometric pattern across the facade. The mechanical systems required weatherproofing that could function through constant movement cycles, with maintenance access designed into the facade structure. The result is a building with a living skin architecture that moves and breathes, transforming throughout the day as those thousands of panels shift position in choreographed patterns across the Bund waterfront. You've just witnessed 42 buildings that collectively cost more than the GDP of Ireland. These aren't just expensive structures, they're architectural experiments that pushed engineering to its absolute limits. China built spheres that shouldn't stand, towers that twist impossibly, hotels carved into earth, and stadiums that look like they're breathing. They engineered buildings on water, in quarries, and suspended in mid-air. They created facades that move, structures that rotate, and forms that seem to exist only in computer models. Every conventional rule about what's structurally possible was tested, bent, and often completely rewritten. The result is a collection of architecture that didn't just change skylines, it changed what the world thought could be built.